All right, everybody, we're looking at problem 67. This is that rocket going up into the air. And they tell you it accelerates for 30 seconds at an acceleration of 30 meters per second per second. So it starts from rest on the ground and accelerates upward until it runs out of fuel. But something that runs out of fuel isn't going to stop right away, because it's going to eventually slow down. This is just like throwing a ball in the air. It will eventually slow down. It'll start off with the same velocity it had here, but it will slow down, slow down, slow down due to gravity, eventually coming to a stop. So this is, I think of this as segment 1 of our journey. Here's segment 2 of our journey, going to that highest point there. And then, yeah, it's going to come back. They're interested in the whole trip here. So we're going to come back down to the ground. And this will be kind of part 3 of our journey, because you've got 3 different motions happening here. You can't analyze it all at once. You've got to work out the pieces and make sure you know what they're asking you for. For instance, in part A, they ask you about the maximum altitude. They want to know how high you are here. Well, that's going to be that max altitude is just going to equal d1 plus d2, my distance that I went up while accelerating upward due to the rocket fuel, and then how far a distance you went coasting as gravity slowly slows you down and brings you to a stop. So we need those two. And let's work out section 1 here. The rocket starts out on the ground at rest. We don't know its final velocity. We know its acceleration is 30 meters per second per second. We're after, we'll call it D1 here. And we do know it does this for 30 seconds. Bingo, you've got enough stuff here to solve for D1. I want an equation that doesn't have the final velocity in it. It's that one. And it's not so bad here to solve for this, because this guy's 0, so he's already gone. Our initial velocity being 0 knocks out the v naught t. And now I just got to plug in. d1 equals 1/2 30 meters per second times 30 seconds being squared. You can calculate that. And it'll come out in meters. Check out your units. It'll work out the second square, knock out a second square here. And the only thing left is meters. So we've got D1. Well, now we need to look at segment number 2 of our journey. And that's a different motion. We need a new VOVAT. I don't know this initial velocity, but I do know that final velocity up here. That's going to be 0 up at the top of this. Oops, where am I? There I am. So I can fill in 0. Whoops, wrong one. I can fill in 0. I know my acceleration is due to gravity, negative 9.8 meters per second per second. And I'm after D2 here. And I don't know how long. I've only got 2 things. I need one more. But that initial velocity that I'm starting section 2 with is my final velocity from section 1 here. So if I knew this, I could copy that up into here. And it's my initial velocity for segment 2. So let's go back to 1 here and say, okay, I need my final velocity. I've got my initial, I've got acceleration, I've got time. Give me an equation without d in it, because that's going to be pretty easy for us to solve. And we get the final velocity for section 1 is 30 meters per second times 30 seconds. You're going to end up with 900 meters per second. That's what's going to go, well, it goes here. But more importantly for us right now, it also goes here. And that gives us a third thing in this VOVAT to where we can go solve for D2 now. And I want an equation that doesn't involve time. So it's this guy. And we've solved several times on this one for D. Let's knock out who's ever 0 here. Our final velocity is 0 because we're coming for an instant to a stop up there. And so you get negative V naught squared equals 2AD divided by 2A on both sides. And you're in business. You can solve, or you can now just plug in to go get D2. Negative of, what is it? Ooh, boy, it's going to be big. 900 meters per second squared divided by 2 times negative 9.8 meters per second. I'll caution you again. Don't lose points for silly calculator mistakes. Put parentheses around that whole denominator, because you need 900 squared to be divided by this answer. And if you don't type it in that way in your calculator, you're not going to get the right answer for that guy. So parentheses around the denominator to be safe. And now that you've got D2, bingo, you can go and get D1 plus D2 and know how high that rocket's going to go, because you've got both D1 and D2 now. All right, now we're ready for part B. Wow, that was just A. How long is the rocket in the air? Well, realize when they say that, we need time T1 plus time T2 plus time T3. I need all 3 of those. So we've got T1. We don't have T2, but I'm pretty sure we can go get it since we have 4 out of these guys. And we're going to need T3. We're going to need to work out another VOVAT yet for section 3. So let's go get T2 here. And I'm going to go ahead and use this guy again. My final velocity is 0. I'm going to get negative V naught divided by A equals T. So subtract V naught first, then divide by A, because you got to undo the multiplying by dividing. And when you plug those in, you're going to get negative 900 meters per second divided by negative 9.8 meters per second. And that gives us T2. We've got T1 of 30 seconds. We just need to go work out T3 and add them all up. I'm going to have to flip to the back of the page here. So, section 3 of this motion. Is just the trip on the way down. So I'm starting at the highest point and I'm working my way down till I eventually smack the ground at some velocity. So we do know our initial velocity for the segment is 0. We know our acceleration is due to gravity, negative 9.8 meters per second per second. And what else do you know? You don't know how fast it's going as it hits the ground. We don't know the time. In fact, that's what we're looking for here. And right now, do I know how high this is? Do I know how far it's displacing? You actually do. Because you know how high the rocket went in those first 2 phases. Well, that's how far it's going to fall now. So, add up our answers from D1 and D2. And that's going to be our displacement. Just one little catch that we'll have to dig into here. D1 should have worked out to 13,500 meters. D2 should have worked out to 41,330 meters for a total of, what's that total come out to? It's going to be those two, 54,000 and 830. I'll just round it to 54,800 meters. Generally in physics, we just round everything to 3 sig figs, so we can round it there and not have to keep carrying all those extra digits along the way. So we now know how high it is. Well, that's how far it's going to fall. 54,800 meters. But notice I said that it's going to fall that far. Its displacement is down. It's negative. So, you've now got 3 items. We can figure out that time. And which equation is this going to be? I don't care about final velocity. It's going to be this one. And it scares you at first, but you realize that's going to be 0. So V naught T is 0. So it's not so bad to just go solve now for D. Or to solve for T here. I got to get rid of the 1/2. I'll multiply both sides by 2. I need to divide out the A. So we'll have 2A over D. That's going to equal T squared. But I can solve for T here by just square rooting both sides. So if I square root T squared, I get T, and I get 2D over A. Now we're ready to calculate our T3. Twice negative 54,800 over negative 9.8 meters per second per second. This was meters. Notice if we didn't have this as a negative in here, we'd have a negative answer under the radical, which mathematically is not a good thing for us. And should tell you, ooh, something's going wrong here. I shouldn't be getting negatives under the square root here. We're not going to be getting imaginary answers out of this. But now you can go ahead and solve for T3, and then go ahead and add up our 30 seconds plus our, well, I didn't calculate that one, but you can, our T2 plus our T3 to get our total time. And you're there. Finally, draw a velocity time graph for the rocket from liftoff until it hits the ground. So here's our velocity axis and our time axis. And let's give this some thought here. It starts out at 0 velocity and accelerates. This part of the journey, something starting out at 0 and accelerating, we've drawn that numerous times. We don't need to put numbers onto this. I'm just after the overall look, but we'll say, okay, it's going to do this for 30 some odd seconds. And it's going to get all the way up to, what did we figure out? All the way up to 900 meters per second. Then it slows down. But it is going to take quite a while to do that. Gravity, hello gravity. Gravity is slowing it down till eventually it comes to a stop. Meaning it hits 0 meters per second for a velocity. Your slope should be much smaller than this one, and it should be negative. If we had numbers in here, we'd need a slope of negative 9.8 or negative 10 on this, and we had positive 30 on this one. You're now at that maximum height, which seems weird because you feel like you're at 0 here, but there's 0 velocity, but you're at the highest point because you're up here. Or better picture, you're up here. You've slowed down to a stop, and you're at the highest point of the whole trip in terms of your height. There we go. And now you speed up, but you speed up in a negative direction. You're getting negative velocities out of this. So you just cross into this side. Negative, it's still the same slope. I'm trying to draw the same slope here. There we go. That's better. It has to be the same slope because the slope of that line is going to be the acceleration, and the whole time, once it ran out of fuel on the way up, and once it's falling down, the acceleration is solely due to gravity. It's slowing it down on the way up, but speeding it up on the way down. But it's still a negative acceleration of 9.8 for that whole time. So eventually, you would hit the ground. Where would that be? Well, you know the total time where that would be. You've calculated it, so you could put that on there. Another way to kind of visualize what's happening here is you could think about the displacement. The displacement, here's all your displacement for the way up. Here would be all your displacement on the way down. You've got positive displacement here, positive area here. You've got negative velocities over here, so you have a negative displacement, which makes sense because it's on its way down. Those two areas should be equal. Whatever displacement you made on the way up, you returned all of it on the way back down. You just went straight up and straight back down to the same spot. All right. That one has a lot in it, doesn't it? All right. Hopefully that helped. Feel free to say, can you explain this part again if you need it?